Hi guys, in this video we're going to be talking about the idea of bond enthalpies, so the energy within the bond. We want to know what it is, how it's related to the type and atoms of the bond, and how it's all related to our enthalpy of reaction. We should be able to use bond enthalpies in calculating out our bond or our energies of our reaction, and we should know what the sign is when we're making and breaking bonds. When we're talking about covalent bond strengths, we're talking about a measure of how much energy is required to break a bond. Specifically, a covalent bond. And this is referred to as our bond enthalpy. So when we have a bond enthalpy, that's how much energy is required to break that bond. So for instance, if we have a chlorine-chlorine bond, and we want to break it apart into two chlorine atoms, we looked at this already, but for 1 mole of chlorine, it is a bond enthalpy equal to 242 kilojoules per mole. So that's how much energy needs to be inputted to break it apart into two individual atoms. Here is a table of some bond enthalpies, and we can see that chlorine-chlorine bond right there at 242 kilojoules per mole. And a lot of different things are going to be taken into account when we're thinking about our bond enthalpies, and they're all going to be given as averages over a bunch of different types of molecules or a bunch of different molecules. So a carbon-hydrogen bond has an average bond enthalpy of 413 kilojoules per mole, but like anything, if it's in a different environment, then it's going to have slightly different bond enthalpies. So this is just used as kind of a tool to kind of determine if a reaction will be endothermic or exothermic, but doesn't give true values. Okay, so we're going to use these tables in order to determine what our energy of a reaction is. So when we think about our enthalpies themselves, if we are breaking a bond, this requires energy. The amount depends on what atoms are involved and what type of bond. A single bond is going to be easier to break than a double bond or a triple bond. As you increase the number of shared electrons between two atoms, you're going to increase the energy that's required to break them apart. Okay? And then if you are making a bond, the value that bond enthalpy is going to be the same, it's just going to be a different sign. So this is going to be negative, and it releases energy. So it's going to be the negative value for the value found on the chart. So for instance, if we take two chlorine atoms and form a chlorine-chlorine bond, this would be an enthalpy of negative 242 kilojoules per mole. Okay, so when we're thinking about bond enthalpies, we have to know what atoms are involved and what type of bonds. Is it double, single, triple, which? And again, this is an average value, so it's averaged over many different molecules. It will not be exact to a specific molecule, but it's a good approximation. When we think about bond enthalpies, we can use them to determine our enthalpy of a reaction by taking into account what bonds are broken and what bonds are formed during a reaction. So you can estimate the enthalpy of a reaction if you know the bond enthalpies of the bonds broken, it's positive, and bonds formed, negative. Okay? To determine our enthalpy of our reaction is going to be the sum of the bond enthalpies for all bonds broken minus the sum of the bond enthalpies for all bonds formed. You can take the values directly out of a table. You don't need to put in a negative value if you're making a bond, or keep it as just keep them all as positive. Note, you need to know the types of bonds formed and broken. So you need to know Lewis structures. And if you have something with resonance, just go with the most stable Lewis structure, or one of the stable ones if you have more than one that have the same energy. Okay, so let's try this out for the following reaction. We have methane plus chlorine gas producing chloromethane and hydrochloric gas. And we want to know what our bond enthalpy values are. So we're going to draw our Lewis structures for everything. So we have methane, and we have chlorine. Going to chloromethane. And HCl. The next thing we want to do is we want to make sure that we balance. So this is a 1, a 1, a 1, a 1, so we're good. But make sure you balance these. And then we look in this table to determine what bonds are broken, what bonds are formed. So our delta H of our reaction will be equal to bonds broken, which are going to be these here, and bonds formed, which are going to be these here. So we need to look. We have 4 carbon-hydrogen bonds. So a carbon-hydrogen bond is 413 kilojoules per mole. So we'll take 4 times by 413 kilojoules per mole. And add that to our 1 chlorine-chlorine bond. So 1 times by 242 kilojoules per mole. And that's all of our bonds broken. And then we'll do our bonds formed. So we have 3 carbon-hydrogen bonds. And then 1 carbon-chlorine bond, which is equal to 328 kilojoules per mole. And 1 hydrogen-chlorine bond, which is equal to 431 kilojoules per mole. And when we do this math, we get a value of 104 kilojoules per mole. As a note, if a bond is not actually broken, you don't need to put it in there. But when you're starting out, it's best to just go ahead and sum up all the bonds on your reactant side, sum up all the bonds on your product side. Let's try another example. We've got N2H4 goes to N2 plus H2. So again, we want to go ahead and make sure we draw out our structures. We've got our N2H4, which looks like this. And this goes to N2 and H2. Okay, next we need to make sure that we have balanced this. So the only one that's not balanced is our hydrogen. If we put a 2 there, and I like to just go ahead and write another one there so that I can keep up with everything very well. Our delta H of our reaction, we've got our reactant bonds, doop, 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 right there. our product bonds. Doop, 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 doop. So we have a nitrogen-hydrogen bond at 391. There are 4 of them total, so we do 4 times by 391 kilojoules per mole. And we're going to add that to our nitrogen-nitrogen bond. We only have 1 of them, and is a single, so it's 163 kilojoules per mole. And then we subtract our bonds formed. So we have a nitrogen-nitrogen triple bond, which is 941 kilojoules per mole, which is why it is so important to draw out your Lewis structures here. And then we have 2 hydrogen-hydrogen bonds, each of which have an energy of 436 kilojoules per mole. And then when we solve for this, we get an enthalpy of reaction of negative 86 kilojoules per mole. This is a negative value, just like we saw in our energy module. So this would be an exothermic process. So if our delta H of our reaction is negative, we have an exothermic process. If it's positive, we have an endothermic process. I want to end talking about bond enthalpy and bond length. Both of them are going to be related to how many electrons are shared between 2 atoms. So as we increase the number of electrons that are shared between 2 atoms, we are going to increase our bond enthalpy and decrease our bond length. So increase that number of electrons shared results in an increase in bond enthalpy and a decrease in bond length. If we think about it kind of like a repulsion theory, as we increase our number of electrons shared, that's going to have less repulsive electrons between, so we kind of decrease our electron-electron repulsion between the 2 nuclei, which is what allows them to get a little bit closer together. Okay, guys, this is it for this module. I will talk to you guys in the next one.